In this video, we'll discuss the divergence of a vector field, and let me start with the definition. So if F is a vector field with components P, Q, and R, then, and assuming that the partial derivatives of these components exist, then the divergence of F is the following quantity. It's denoted div F, and it's the following sum of partial derivatives. So dp over dx plus dq over dy plus dr over dz. So this is the divergence of F. And it might be useful, one way to remember this formula is that, again, just like with curl, treating Nabla as a vector-like object, and noticing that if this is Nabla, then the divergence of F is simply the dot product of Nabla and F. Formally treating as Nabla as a vector, formally, this dot product will give you the right-hand side of this equality. So that's one way to remember the formula, and this is somehow a alternative notation for the divergence of a vector field. Let me give you an example, ask a question. So take the following vector field, f of x, y, and z. Its first component is x times z, its second component is x, y, z, and its third component is minus y squared. Your task is to compute the divergence of this vector field. So pause the video and input your answer below. Okay, I hope you paused it and used the definition to compute the partial derivatives of the components with respect to x, y, and z respectively, and found that the first component differentiated with respect to x gives you z, the second component differentiated with respect to y gives you x times z, and the third component differentiated with respect to z gives you 0. So its divergence is z plus x times z, or 1 plus x times z. Okay. One important result is that a theorem is that the divergence of a curl is always 0. So if you take the divergence of the curl of some vector field, which using Nabla could be written as follows. So Nabla dot Nabla cross F is identically 0. And the proof is very simple. You just have to use the definition of curl and divergence, write this expression out in using components, and you will see that it is identically 0. Each term will be cancelled by some other term in this expression. So the proof is left to you. Let me give you another example or another question. So let's say that we look at the same vector field that we had before, and you are asked to show that this vector field cannot be obtained as the curl of any other vector field or any vector field. Okay, so pause the video and explain why it's the case below. Okay, I hope you paused it and realized that because we have this theorem which tells us that the divergence of a curl is always 0, and this vector field has a divergence that is clearly not 0, there cannot be a vector field G for which this would be the curl of G. Okay, so the example F is not curl G for any any vector field G, because the divergence of F is not zero. Okay. So to finish off, let me just mention some vector forms of Green's theorem that we've seen before, and it's stated that the line integral of p dx plus q dy along some simple closed curve C can be evaluated by taking the double integral of dq over dx minus dp over dy over the region that the curve encloses. Now this theorem, Green's theorem, can be formulated using vector fields and the curl and the divergence of vector fields as follows. So imagine that we take the vector field F to be P times I plus Q times J, and giving it as third component 0, then its curl will be nothing but this expression dq over dx minus dp over dy times the basis vector k, in fact. So if you compute the vector, the curl of such a vector field, you will get exactly this. So you can see that the integrand of this field, of this integral, is just the curl of f, well, multiplied by a dot product with the basis vector k. Okay, so what you can say that the left hand side is nothing but the line integral of f along the curve. So Green's theorem can be reformulated as follows: the line integral of f along the curve C is the double integral of the curl of f dot k over the region that C encloses. So this is one way of reformulating Green's theorem using the curl. There is another way of rewriting Green's theorem, and that uses the divergence, and that would be the following. So the vector, the line integral of f dot n along C, this closed curve, is the same thing as the double integral of the divergence of f in the region that is enclosed by C. So that is also Green's theorem. For details, you can look up this section of the book, textbook, and you will find these derivations going from Green's theorem to this form and to this form. So these are called the vector forms of Green's theorem. Okay, I hope you enjoyed this video, and I'll see you in the next one.